Hi, my name is Patrik, and thank you so much to the organizers for allowing me to give this presentation on behalf of the BESIII collaboration. So the topic that I'm going to talk to you about is CP violation studies of hyperon anti-hyperon pairs, which we measure with the BESIII experimental setup. So let's get started. So the outline of my talk is that I'll give you a brief motivation. I'm going to just give a short slide on the BESIII experiment. And then I'm going to jump straight into results that we have obtained studying single weak decays. Then I'm happy to be able to present to you some new results that we have just released onto arXiv and submitted for peer review. And it's the first weak phase measurement of baryon decays. And finally, I'll end with a summary and outlook. So we're discussing the topic of CP violation. So we've known about this since the 60s, and now more than 50 years. Still, we have only been able to confirm it in meson decays. In the standard paradigm, the universe was created with equal amounts of matter and antimatter at the Big Bang. And the present CP violation, which is explained by the standard model, is not sufficient to explain the asymmetry that we see. And from Sakharov, we know that baryogenesis requires both C and CP violating processes. It's also very important because CP violation is such a subtle effect. So to understand how it functions and works in the flavor sector, we want to study it systematically using different hadronic systems and with complementary methods. So in the strange sector, the most precise probe is studying the ratio of the direct to the indirect CP violations given by the epsilon prime divided by epsilon. Experimentally, it's been measured to great precision by 2 experiments. And when you compare the average value of those results to the standard model calculation, you see that they are in good agreement. However, there are 2 points to make. One is that within the uncertainties, there's still some room for beyond standard model contribution. And in addition, the standard model calculation has been difficult to obtain due to the fact that one is dealing with partial cancellations of QCD and electroweak penguins. It's therefore important also to study this type of CP violation using other types of probes. What one can do is to study hyperon two-body decays. Here we also test direct CP violation. In addition, there have now been some recent methodological breakthroughs which allows us to make very precise measurements of these decays. The way that we study CP violation in hyperon two-body decays is through comparisons of asymmetry parameters. But asymmetry parameters are closely linked also to the polarization. So the polarizations of hyperons are experimentally accessible through weak parity violating decays. And so the most common two-body decay that's been studied is lambda, which decays into a proton and a pi minus. And these hyperon two-body decays are self-analyzing, which means that if you study the angular distribution of the daughter baryon, in this case the proton, they are emitted according to the polarization of the mother hyperon. And so if you have the angular distribution of the proton, you have a factor which depends both on the polarization of the mother hyperon, but also on the asymmetry parameter. And it's the asymmetry parameter that we use to make tests of CP violation. So what you can do is then compare the two-body decay of the corresponding antiparticle, so the ΛΛbar decaying to a proton bar pi plus. Now, if CP conservation holds, the asymmetry parameter of the hyperon decay is negative to that of the asymmetry parameter of the corresponding anti-hyperon. That means that you can make a comparison using this ACP observable. Now, I discussed the case of lambda decaying into a proton pion, but this test is not limited only to this two-body decay, but to all non-leptonic two-body weak decays. It's at the BESIII experiment where we make these measurements, and it's well suited for make these types of CP precision tests for many reasons. It's a multi-purpose detector, so we can measure both charged and neutral particles with very good resolution. We have near 4 pi angular coverage, which is important for efficiency. We have symmetric particle anti-particle conditions. It's an E+E- experiment, which means that we have low hadronic background. We've been taking data since 2009, and that means that we've studied systematics extensively, which means that they are controllable. In addition, we have the world's largest Chemonia data sample that we've collected. For our purposes today, I'm talking about the ＪPSI resonance, and we are literally a ＪPSI factory. And at this energy, the full baryon anti-baryon octet is kinematically accessible. So the formalism for an E+E-, which produces a hyperon anti-hyperon pair, either via a photon or in this case via a ＪPSI resonance, consists of 4 unknown parameters which have to be determined and 5 helicity angles which are measured by the experiment. And the 5 angles are the outgoing scattering angle of the hyperon, and then 2 helicity angles for the decay particles of hyperon and anti-hyperon respectively. The 4 parameters which needs to be determined are 2 production parameters, so 1 angular distribution parameter and 1 relative phase. And this relative phase is connected to the polarization, and that's very important for these single weak decays. Then there are 2 decay parameters, the symmetry parameter for the lambda proton pion and a corresponding asymmetry parameter for the antiparticle decay. Now the formalism can be structured into 3 parts. So 1 unpolarized part, 1 spin correlated part, where the asymmetry parameters are multiplied together, and the polarized part, where the symmetry parameters are decoupled from each other. It's this term which is important when you want to determine alpha and 𝐶bar separately. And this only happens if this sign of the relative phase is non-zero, which translates into the statement that in order for us to be able to measure alpha and 𝐶bar simultaneously and directly, this has to be non-zero, which means that the lambda and lambda bar pair have to be produced in a polarized state. This was measured by us in 2019, where we studied the ＪPSI to lambda bar. And here to the left, you see the effect of a non-zero polarization as a function of the cosine scattering angle of the lambda. Had there been no polarization, we would have seen this to be at the flat line, but this shows the level of polarization, which can then be translated to a maximum polarization of 25%. So this was the first measurement of hyperon polarization at the ＪPSI resonance, published in Nature Physics. Now the fact that this was non-zero allowed us for a direct and precise measurement of the asymmetry parameter of lambda and lambda bar decay. And what was astounding was the asymmetry parameter turned out to be 17% larger compared to the old assumed value of 0.642. And this is important, this parameter, not only in and of itself, but the fact that many experiments use this at face value. So that means that either those results, which depend on the alpha value, would either have to be corrected or remeasured. Now, inspired by our measurement, there was a remeasurement using old class data, and they found a slightly lower value of 0.72. So now the current PDG value is the average based on these 2 values, which are mutually incompatible with each other. So in order to clarify the situation, if it's the lower alpha value which is correct or the larger one, we need more experimental input. Now the fact that we could measure the alpha lambda and alpha lambda bar simultaneously meant that we could also do a direct test of CP violation. And this allows us to make most precise test of CP for the lambda to proton pion decay. Now, the fact that these particles are produced polarized meant that we can also study other types of two-body decays. And next in line was the sigma plus decaying into a proton pi naught. Also here we found that they were produced polarized. And this allowed another CP test, this time the first CP measurement for any sigma decay. This is consistent also with the standard model expectation. But you see that the fact that these are now produced polarized allows us to make these direct CP measurements, which is a huge methodological breakthrough. Now coming to the result that we just pushed to arXiv, which is the study of weak phases and CP-symmetry tests in sequential decays of cascade particles. And coming now to the asymmetry parameters, I talked to you about the alpha parameter, but in fact there are two more CP-odd decay parameters given by the beta and the gamma parameter. If you look at the definition of the beta and gamma, they are dependent on the alpha parameter and the phi decay parameter. Now experimentally, the phi and alpha parameter are nearly independent of each other, so what's measured is the phi and alpha in experiment. So what does this alpha and phi parameter mean? Given this picture here of a cascade which is produced with some degree of polarization, which then decays into a lambda and a pion, the lambda is also polarized, and it has then both the transversal and the longitudinal component. And the longitudinal polarization is then governed by the alpha parameter, while the transversal component is governed by the phi parameter. Now, given that phi is independent from alpha, we can make also an independent CP test by comparing the phi value of the cascade decay to the phi value of the anti-cascade decay. Now, the symmetry parameters is the interference of the two possible amplitudes, a parity violating and a parity conserving. And these are complex entities. The asymmetry parameters describe the relationship between the two decay amplitudes. What you can notice here is that they contain a strong phase and a weak phase. And coming now to the ACP observable, which I discussed before, to lowest order, this is dependent on a strong phase difference, which is CP conserving, and a weak phase difference, which is possibly CP violating. And we're interested in the weak phase difference here. Now, the strong phase difference is known to be small, and that means that the ACP observable is suppressed. Another way of rewriting this is given here in this frame. So the ACP part is governed by the value of sine phi, whereas the delta phi is governed by cosine phi. So if phi is small, this is approximately 1. And that means that this suppression factor, which is present in the ACP, is not present for the phi CP test. Now, this was already discovered 35 years ago by Donahue and collaborators, but it hasn't been measured up until now. So the formalism for studying the cascade sequential decay is the same as for the single weak decay, but it's slightly more involved due to the fact that we have decays which are happening in sequence. But the formalism also includes polarization, entanglement, and the fact that we have sequential decays, which are given here in these A parameters. Compared to the single weak decays, we had a 5-dimensional phase space. Now for an exclusively measured ﷺ, we have a 9-dimensional phase space, and given by 9 measured helicity angles. In this process, there are also 8 free parameters, which are determined by the maximum log likelihood method. And here in red, you can see the parameters which have never been measured before. The analysis that we made is based on 1.3 billion JPSI events. And in the end, after all selection criteria, we have 73,000 exclusively measured cascade minus cascade bar plus events. As you can see here in the right plot, we have a very low level of background. And note the logarithmic scale. We also did extensive systematical studies, and we found that they were small and coming mainly from the selection criteria. So here are the results that we obtained from the exclusively studied cascade minus cascade bar system. And this system is really exciting because contains so much physics information. So first of all, we make the first measurement of the cascade polarization. We make the first direct determination of all the cascade minus cascade bar decay parameters. Now previously, other experiments only measure the product of alpha cascade, alpha lambda, but we measure them directly for the first time. In addition, we make an independent measurement of the alpha lambda and alpha lambda bar asymmetry parameters, and our results are in excellent agreement with the previous BESIII result. What's interesting to note is that this work was based on roughly 70,000 exclusively measured cascade bar events. But we obtained roughly the same precision as the BESIII measurement of j-psi lambda lambda bar, where they had a 6 times larger data sample. Since we have all the information of the decay parameters, we can make the first extraction of the weak phase difference for any weakly decaying baryon. And these are the results that we obtain, and they are consistent with the standard model expectation. What's exciting here is then that we have now a new method for directly measuring the weak phase. In addition, we can perform 3 independent CP tests in a single measurement. All of them are consistent with the standard model. And for the first time since its proposal 35 years ago, we can also test CP using the decay parameters phi and 𝐵. Now, since CP violation seems to be conserved at this level of precision, we can combine the decay parameters of phi and 𝐵 into a single reading, so taking the average. Interesting to note here is the uncertainty. And so based on 140,000 events, we can obtain the same precision for these phi parameter as the hyper-CP experiment, which measure decay parameter phi using 3 orders of magnitude larger data sets. So they used 140 million cascade minus events, and we obtained the same precision using only 140,000 events. Because of the fact that we can measure the average value of phi, we can also extract the strong phase independently. And so our strong phase measurement is compatible with the standard model expectation. However, we are in tension with the hyper-CP results. Summary then. I want to convey to you, and I hope that I have, that the BESIII has a very rich program of testing CP by comparing hyperon and anti-hyperon decays. We have now for the first time presented a novel model-independent method which exploits spin entanglement in sequential weak decay chains of the cascade minus. Now the method that we have used can also be used in other types of entangled pairs. So it's not restricted to just strange baryons. But we can see that this method can be used, for instance, at Panda, BESIII, and the future planned super tau charm factories. We have presented to you the first measurement of the weak phase difference for any baryon decay. And in addition, we presented to you the first results of testing CP in a completely new way by comparing the decay parameter phi to 𝐵. Thank you so much for your attention, and thank you again to the organizers.